Welcome back to the Electronics Inside, the show where we tear down tools, toys and appliances just to find out what's inside. I'm David, and in this episode you will notice that I have three separate devices here, all powered by a single power lead and a network switch. That's right, we're going to be covering the miracle that is power over Ethernet. We'd probably better start with some really low-level stuff, because I suppose not everybody is actually familiar with what Ethernet is or really how it works or is distributed. Okay, so Ethernet has actually been around since the mid-1980s, and originally it started out with coax, and I think it's a D15 connector, but very much later moved on to twisted pair cable, and that's what I've got a couple of samples of here. Now, this is not to say that other methods of connecting to Ethernet don't exist. There's obviously fiber and wireless and others, but cabled twisted pair Ethernet is by far and away the most common. And that's not even mentioning the Ethernet over single pair, which basically is how internet is distributed around most of the world over old copper phone lines. But that's getting way into the weeds. Let's focus on twisted pair cables. So here I actually have a sample of a Cat5e cable, and this is a Cat6a cable. This is actually a low smoke zero halogen version as well, which is a whole other cable spec thing. Don't worry about it, I've probably gone into too much detail already. Now, both of these have twisted pairs. If I strip the outer sheath off the UTP unshielded twisted pair cable, you will see a little nylon tensioner taking the tension out of the cable, and 4 twisted pairs. So it's 8 individual cores, and I have a twisted pair of white, blue and blue, white, orange, orange, white, green, green, and white, brown and brown. Notice that they aren't all twisted the same. The orange has a tighter twist than the brown, and depending on which standard you're using is to which pair you're using. If you're doing 10 or 100 megabit Ethernet, which was common and still is quite common with a lot of devices, to be honest, up to, let's say, the late noughties, 2010-ish, you would probably only have used 2 pairs in this. And that was enough to get you 100 megabit. If you want to go to gigabit, so 1000 megabits per second, you needed all 4 cores. And the rate that they're twisted, the size of the conductor, and the purity of the copper makes a big difference. So that's Cat5e. This is Cat6a. One thing I've never actually worked out, and I probably should have done having started this episode, is what happened to Cat4? Because Cat3 is commonly classed as the loosely twisted pairs you get in phone lines. And you've got Cat5, Cat6, and there's Cat7 and Cat8. What happened to Cat4? So this is a foil twisted pair, or screened pairs. And you see we've also now got a drain wire. So this copper wire will help take the strain, but it also should connect to ground at one end of the cable. So each of our twisted pairs is now wrapped in foil. They are thicker gauge cables, but otherwise the same coloured twisted pairs. So again, you see you've got the different twist rate, but you've got larger conductors and purer copper. Now, you can get both 5 and 6 in foil twisted pairs, or screened with an overall screen that wraps all 4 of them together. Now, the screen tends to protect the cable from external interference from other electrical wiring or magnetic influences. The individual wrapped pairs tends to be for the cable itself to protect each pair from interference from each other. Now, a Cat6 cable should do 10 gigabit connectivity up to, I think it's 40 meters. Cat cable will be good for about 92 meters, but a Cat6 cable will only do gigabit at 92 meters. If you're using this full twisted pair, you can get up to a 10 gigabit over the full 92 meters. 92 meters, I think, is 300 feet. And it's really funny because these cables are so drastically different in outside diameter and weight. If you pick up a box of 304 meters or 1,000 feet of Cat5e, you wouldn't think twice about picking up 2 or 3 in one go. If you get a box of Cat6a, one box is enough. And the cost difference is drastic as well, and it's just the weight of the material involved. So anyway, 4 twisted pairs. Like I say, for 10 and 100 megabit, you only use 2 pairs or 4 cores. If you want to go gigabit or higher, you use all 4. That becomes important later when we start talking about the amount of power delivered over Ethernet. So when we're talking about power over Ethernet, we are talking about field devices or powered devices, PDs, in the field that require some power to operate. And rather than having to run extra electrical wiring out to them and a data cable to them, then have a switch mode power supply locally to the device that can then provide the 24 volts or whatever it needs to operate, you can run that power and the data down a single cable and have a single switch mode power supply, bear with me, I know where I'm going with this, in a rack, in a data center, in a cupboard somewhere that can supply 16, 20, whatever devices with all the power they need. Makes the field devices cheaper, makes your installation cheaper. It means you can use cheap Cat6 cable that can be installed within reason by any competent person. You don't need an electrician to come in, do the installation and the testing. It's amazing, and frankly, I wish there were more devices that used PoE, power over Ethernet. The switch, or the device providing the power, is called a power supply equipment, or powered supply equipment. And that's normally a switch, but you can get other devices, and I would typically term these PoE injectors, which will take an Ethernet signal, just a plain one from any normal switch, and then add the power overlaid on that network cable. You have to be slightly careful because the early PoE standards came from about 2003, and those came in an A-type and a B-type. Now the A-type worked very similarly to the modern standards, where you cleverly overlay the power and the data on the same cores of the cable. But the B-spec basically made use of the unused for 10 and 100 megabit cable cores. So you had 2 pairs doing data and 2 pairs doing power. Not a problem, all the time you had those spare cores, use them. But when you didn't have those and you had a device expecting gigabit, and you actually ran the risk of shoving 12 or 24 volts down that cable. So there are standards, and the standards should negotiate and check before they send power down. Works a little bit like power delivery does now, but wasn't always the case, and isn't always the case for cheaper, less official and certified devices, let's call it that. Types of powered devices, I mean, you've got the obvious, you've got cameras, you've got wireless access points, voice over IP phones, all sorts of other devices, and the coolest one, which nobody ever seems to list anywhere where they're talking about PoE devices, is Raspberry Pi 3 and 4. You can get Raspberry Pi 3 and 4 hats that do power over Ethernet, which is awesome because that means you could run a single Cat5 or 6 cable from a PoE switch to wherever your field device or your Raspberry Pi is doing some sensing, some actuation, whatever it might be, and you don't need to run separate power. How cool is that? I think at some point we should make a point of doing a Raspberry Pi project that requires the PoE hat, because it's cool, why wouldn't you? Should we start by having a look at what makes the switch or the power supply special? This is a 16 port switch, but it can only deliver PoE over the first 8 ports. You do get the full size 19-inch 48 port switches, but my goodness, they are physically big and they will pull 3 kilowatts off the main to deliver PoE to each port. And normally the fans, well, you'll know about it. I would love one day to get hold of one of the insane sort of core switches you might use in a data center. This will do 16 ports at 1 gigabit, but that doesn't necessarily mean it can deliver full 16 gigabit all at the same time. It will have what's called a core bandwidth feature, which is sort of how much onboard processing it can do to allow the network traffic to fall through. This one is actually capable of doing the full 16 port, but within this range you could get up to a 48 port, and it actually had a limited bandwidth. I think it was like 30 gigabit per second throughput. But when you get up to big data center stuff, there is an Ethernet standard now that goes up to 400 gigabit per second. And you look at the hardware inside these switches and they look more like high-powered servers than they do normal switches. If anybody knows where I can get one of those for a teardown, I think it'd be awesome. Ooh, a lot of dust in here. Now, it's not a surprise that there is a large switch mode power supply in here, and that, I reckon, is what this fan is probably protecting, because the actual network switching is not too high powered, in this at least. I mean, we've got some little heat sinks on it, which will be looking after some of the switching components, but for the most part, it's pretty low power. I'm actually going to clean this out before we carry on. Just for simplicity's sake, it's a switch mode power supply. Shall we just pop the cover off of that? It's everything you've come and known to expect from a switch-away power supply. Don't think we need to go too far into that. Ethernet, a lot like USB Type-C, which I know we've touched on. If you followed the iMac G4 rebuild I did, we talked about USB 3 using differential pairs in that. And that essentially increases the stability of a high-speed switched network bus by sending the same positive signal and negative signal over a pair of the same resistance. So when you get to the other end, you have twice as much chance to a reference ground of understanding what that differential signal would be. For normal signaling purposes, that doesn't need to be much. It could be like 1 volt, 2 volts. And that's more or less how the pairs of Ethernet work. But imagine now that instead of going between 0 volts and 1 volt either way, that actually this pair have an overall potential to ground of, let's say, 12 volts. And another pair have a potential of negative 12 volts. It's like a center tap transformer. How Americans get 120, 120 and 240 volts in their kitchens. There you go, that is the networking bit out of a network switch, funnily enough. So again, fan, power supply. I'm going to put them to one side because they're less interesting for what we're doing. Wow, this needs some cleaning up. So you see we got 8 ports and 8 ports. These 8 ports are the PoE ports, and you see they've got much bigger ICs driving the back end of it. And I've got smaller ones driving these 8 gigabit ports up here. There's sort of minimal power management actually on this switch. And bearing in mind it's providing power to these 4 switches and these 8 ports, but it's also got its own onboard management that it needs to provide power for. So I mentioned earlier a PoE injector or a power over Ethernet injector. This is possibly the lower end of the quality spectrum, but it does function. I can say that at least. And it's just a switch mode power supply on a UK plug. I've got LAN and PoE, so you plug your normal network in there and then your device to be powered by power over Ethernet gets Ethernet there. And the LAN is just overlaid. This device doesn't even see the network traffic. It's just handling it as little more than noise on its 12 volt signals. So that's a PoE injector. You get nicer ones, but this is one I happen to have. So I have here a Sanance camera. It takes PoE or there's a barrel jack and you can provide this with 12 volts. I have not managed to get this working other than the little power LED indicator on the RJ45 lead to flash. But we're here to take it apart, so it doesn't matter if it works or not. Now, we won't ever talk about how this came apart, but we're also just going to ignore the snap screw in that hole. Inbuilt silica gel pack. I guess if this is an outdoor camera, then you would want to make sure that any moisture gets wicked up and stops you steaming up the lens. And you can just about make out on here, there is actually a gasket. So this is a waterproof camera, should keep the weather out nicely. So coming up this cable, remember I said you've got the 12 volts and you've also got PoE as an option. 2 leads here, positive and negative, this black and red, which comes straight up to the camera. So if I pull that out, that actually goes straight to the back housing. And I'm guessing that will bell out to there if we tested it. But you see we've got this board, which must handle PoE. Okay, so remember I said that if you're doing 10 gigabit, you often have the foil wrapping, certainly over certain distances, to keep the signal from each of the pairs separate. Now, the reason you twist those is the differential pair. So if you've got that positive and negative charge, they are offsetting each other's magnetic field on a twisted pair, which means the signal doesn't leak out, but it's also less sensitive to interference. And what they've done here is use this horrible stranded and not twisted pair cable. It's just a mess of 8 cores. Now that means you'll get what's called crosstalk or near-end crosstalk, and that interferes with signals. And this is supposed to be an HD camera, and I'd be surprised if this doesn't really affect the networking performance of the connectivity in this camera. So we have this little board here, which is broken out 1, 2, 4, and 1, 2, 3, 4, 5. So this must have, oh, okay. So the LED is actually taking feedback from the cable. It's not an IC in here. So there's an extra core that sends power back to this LED. That makes sense. Then we've got the 2 plugs onto this board. The networking will just be throughput, and this strips the power out and then sends that as clean power onto the camera board. Now, we're not particularly interested in this context in the camera itself, but you know, there's going to be a lens, a sensor, a CCD probably. We've got an IR array, we've got an LDR, a light dependent resistor. The sensor you can probably make out on the back of this board. It's where the white patch on the back of here is. This little board is doing all the PoE heavy lifting. I wonder if this is actually like a off-the-shelf board you can... Oh look, they've labelled all the pins and everything. Then it's got the option for another connector there, which it labels as 12 volt and ground. I wonder if I plugged this into another application, whether I could get 12 volts out of this and use that as a PoE breakout board. So the other device that we've got a hold of to look at here is a wireless access point. And these are another example of things you want everywhere, but you don't want to have to run specialist power for, and you want your not electrically qualified IT team to be able to install as and when they need to. These, your router at home that connects you to the internet has a Wi-Fi access point built in. Think of them as smushed into a single box. But if you wanted to add another one, you don't need the whole routing component with it. You just need the access point, which is one of these. This is made by a company called Ubiquiti, and this is their product called Unify. So let's crack it open. Whew. There you go. Those 2 points were convincingly fitted. Gorgeous little board. And look how funky those antennae are. They are awesome. I've never seen one like that before. Interesting that having seen what the inside of the switch and the little PoE board off the camera look like, I'm instantly looking at these two ICs going, well, that's clearly the PoE switching, isn't it? Interesting that you've actually got external antenna points as well on here. Something about the layout of this board is really cool. These traces up here, which just sort of take nearly this quickest line straight away from these main ICs. It's like they're not following normal rules of PCB layout. We can see all the bits. I think it's time I did some searching for part numbers, and I'll get back to you. Okay, spent a bit of time really looking around these PCBs and examining the parts and looking up part numbers, things like this. It's actually kind of more interesting than I thought it was going to be. I thought there would be just an IC that handled the PoE and the Ethernet and the integration of the two, and it kind of happens like that, but not really. So all of these big packages all along here, these two on the Wi-Fi access point and this one over here, are all essentially the same object. They are big inductors and magnetic isolators which take the Ethernet signal and pass it through a series of inductors that go between the differential pairs and then to ground to give you that clean signaling. But what they also do is provide an opportunity for you to have that isolation if you're not using power that is being thrown down the line. You don't have to do anything with the sort of additional voltage that's applied between these differential pairs. But what it also gives you at this point is the chance to use all these power electronics down here, all these diodes, to inject additional power onto those inductors, those magnetic coils. And then you've got your different voltage differentials, your plus minus 12 volts, to give you the distribution with the Ethernet signal inserted over the top magnetically. It's actually a much lower level process than I thought it would be. I thought there would be an IC doing all this work, but it's not. You just throw the voltage in a protected, safe way on top of the Ethernet signal. That's kind of cool. That's how you get the power on there, and you just kind of repeat that process but in reverse on the other side. So on the access point, you've got your two Ethernet magnetic ICs, but you've got this big can over here, and that's taking all of the power and the signals out of here and stripping that voltage off of it. If we look on the other side, you can sort of identify a lot of that power circuitry up here. And then it gets to use that on the board however it sees fit, which is really cool. And similarly up here, much simpler and cheaper implementation, but the same idea. You've got your Ethernet, your power electronics thrown on the back of it. And that's really cool. And yes, I tried looking up this board as a separate part number, couldn't find it, but I'm pretty confident, having looked at it, that I could use that for a different project. One thing I did find that was really interesting, the datasheet for these magnetic packages is actually only rated up to 100 megabit, and this is a gigabit switch. So Netgear either had additional approval from the manufacturer and certification body, or they are being a little cheeky on this device. Now, don't get me wrong, it's an old device. I don't believe it's likely to be in circulation anywhere that's important, but interesting all the same. Power over Ethernet is a great technology, and bearing in mind these days you can throw 50 to 70 watts down a Cat cable. You know, that's enough that I could supply an LED downlighter quite comfortably with enough power from one of these things. Is it time that we gave PoE more consideration for other distribution for small power loads? I mean, there is plenty of energy, 50 to 70 watts on modern PoE kit going down these cables. I could comfortably run an LED spotlight or downlight off of that. Is it time that we had a project trying to power more things over PoE? Thank you so much for joining me. I really enjoyed this one. I hope to see you on the next one.